Welcome back to Low Academy. Today we'll be covering a solution to a math problem that was presented in one of my AP literature books, All the Light We Cannot See. It's a brilliant novel about a young German boy named Werner and a blind girl named Marie Le. It's a really great novel filled with lots of imagery and lots of symbolism. Shout out to my English teacher for introducing me to this novel. She's pretty cool. Now, the problem in question happens on page 153, where Werner is asked to solve a problem. Now, the math in this section of the novel usually falls under the radar for readers, because the novel never really explains what the equations are, why they're important, and how did Werner solve it. But today, I'm going to explain each of these formulas and solve it. Now, in the chapter, Hauptmann gives Werner this formula and asks what it does. Well, based on the looks of this is a trigonometric identity. Also, because this trigonometric identity doesn't have a name, I'm going to name it myself. So I'm going to name this Werner's identity. Now, Werner's identity doesn't mean anything if I don't explain what each of the letters mean. So here's a triangle, and here's how it's labeled. In this case, this is what each of the letters represent. L is the length of the triangle, A and B are the angles, so tangent A, tangent B, these are both angles. And D is the height of a triangle, also known as the distance. It is the distance between the bottom of the triangle to the very top of the triangle. So, what does Werner's identity help us do? Werner's identity helps us solve the length of a triangle. As you can see, the length is on one side of the equation. If we know the distance and we know the angles, we can use this equation to solve for the length of the triangle. Now, this wouldn't be a Low Academy video without me explaining why, so I'm going to do a quick derivation of this formula. So because this is a non-right angle triangle, we can't use our normal trigonometric functions here. But if we split the triangle in half this way, we can split it into two different right angle triangles. Now, to note, this distance here would be D. This distance, also D. This would be angle A, and this would be angle B. Now, because L is split in half, we can't call this L anymore. This distance is no longer L. Neither is this. So this will be L1 and this will be L2. Because we're splitting in half, there's two different sections of L, so L1 and L2. Therefore, we can also write L1 plus L2 equals L. Great, so how do we get Werner's identity? We get Werner's identity if we can solve for L1 and L2 respectively and add them up. So in each of these triangles, we have to find a way to express L1 using the information that we're given in this triangle. So let's see what we can do here. So we have the opposite and the adjacent of the triangle. I wonder if there's a trigonometric identity that uses both of those. The tangent. So let us write it out. Tangent of A is equal to the opposite. So opposite here over the adjacent, which is L1. Okay, and let's do the other side as well. So tangent of B is equal to the opposite, which is D over L2. So now all we have to do is solve for L1 and L2 respectively. We can just swap these two, so we get L1 is equal to D over tan A. And we can also swap these two. So we can get L2 is equal to D over tan B. And now, if we remember here, L1 plus L2 equals L. So all we have to do is just add these two up. So if we get L is equal to L1 plus L2, that is also equal to D over tan A plus D over tan B. And this is Werner's identity. So here's the proof behind Werner's identity. Now that I fully covered what this formula does and why it does what it does, here is the problem presented in the chapter. So let's say this guy is Werner and this guy is Volkheimer. And they're trying to figure out how far they are from an enemy radio broadcast in order to eliminate their target. Now, if we have a situation like this, we can actually form a triangle. So the triangle will look something like this. Now, if we have a triangle, we can label it like this. So we have the length here, which is the distance between Werner and Volkheimer. Great. We also have the distance of how far the source is from them. They also have angle A, which is the angle between Werner and the source, and angle B, which is the angle between Volkheimer and the source. And if we look carefully, we already have an identity that relates all these things, called Werner's identity. But here is our problem. Even though we have a great formula that relates all of this stuff, it actually solves for the completely wrong thing. Werner's identity solves for length. It assumes you know the distance. What the Germans are most interested in is the distance between them and their target, because they already know the length between the 2 points. Because if you're Werner, you can easily go to Volkheimer and say, hey, can you walk 3 kilometers east from here? And just like that, they would already know the length. The thing that they really need to figure out is the distance between them and their target. So, the problem becomes, can you create a formula that solves for distance? Then, the problem becomes, isolate for distance. So what Hauptmann was trying to ask Werner, based on this formula you have here, can you solve for D? So that was the problem. So now let's actually get into how Werner solved this problem. Werner was able to do it by introducing 2 other trigonometric identities. First, Werner used the sine addition identity, which is sine A plus B equals cosine A times sine B plus cosine B times sine A. So that was the first identity he used. The second one is the tangent identity, where tangent of theta equals to sine theta over cosine of theta. Through using these 2 formulas, he was able to solve for D. So let's get into a solution. Let's start off with Werner's identity. So L is equal to D over tan A plus D over tan B. Now, the first thing we're going to use is the tangent identity, where tangent of theta equals sine theta over cos theta. We're going to change this tangent into a sine over a cosine. So let's do that. So we have L is equal to D over sine A over cosine A plus D over sine B over cos B. Okay. Now this is a fraction on a fraction, and it's pretty disgusting, but we can simplify this a bit. This is really just D divided by sine over cosine. So we can just flip these around. We can flip these around and multiply. So this will simplify to D cosine A over sine A plus D cos B over sine B. Now this looks pretty bad still, but we can simplify it a bit further. We can multiply both sides by sine A. So if we multiply sine A, we can cancel this out. So let's do that. So we get sine A, L, is equal to D cosine A plus D cosine B over sine B times sine A. Now we still have a fraction here, so let's multiply both sides by sine B. So multiply this by sine B, and we multiply this by sine B. So this can cancel out. So we get sine B sine A times L is equal to D cos A sine B plus D cos B sine A. So what you can note here is that there's two D's. So we can factor this out. So we get D times cosine A sine B plus cosine B sine A. Great. And all of that is equal to sine B sine A times L. Now this monstrosity, what is that? Well, if we look carefully, cosine A sine B plus cosine B sine A, that's exactly the same as the formula up here. So we can replace it with sine A plus B. So let's do that. You get sine B sine A times L is equal to D sine A plus B. Awesome. And now, since D is multiplied by sine A plus B, we can finally isolate for D. So we can do that by dividing both sides by sine A plus B. And these will cancel out. And we get our final formula. If we rearrange some terms a bit, we get L sine A sine B over sine A plus B is equal to D. And this was what Werner was able to figure out. So here's the grand formula, and now let's see it in practice. Once again, we have the same scenario out here. We have Werner out here, and we have Volkheimer. And let's say they agreed to be at a distance 3 kilometers from each other. So here is an unknown source. Here's our triangle. So Werner measures the angle between him and the target, and he finds out that it is 48 degrees. Volkheimer does the same, and he finds out that it is 37 degrees. Now if they want to solve for D, they can use Werner's new formula here. All they have to do is just plug their values in. So let's say in this scenario, L would be equal to 3, sine A would be sine 48, B would be 37, so it would be sine 37, over sine A plus B, so sine 48 plus 37. So that would just be 85. And that will equal D. So if we plug this into our calculator, we would find out D is 1.3468 kilometers away. So if you're Volkheimer in this situation, you would know what direction and how far your enemy is. So you can simply head to the source of the target and brutally eliminate them. This is a glimpse of how mathematics can be used in wartime to solve problems and even take out targets. Now, it kind of sucks that human life was lost as a result of this formula, but I'm not here to question the morals of it. I just think the math is kind of cool. Anyhow, I hope I explained this section of the novel, and this is Low Academy, signing off.